Today we're going to be learning how to name chemical compounds. Now there's two types of chemical compounds, eventually three, but two right now that we're going to have to know how to name. Ionic compounds and covalent compounds. Now, the way to tell them apart really quickly, ionic compounds are when a metal and a non-metal bond. You can use the periodic table, the left of the staircase and the right of the staircase. Covalent compounds are between two non-metals, same or different, doesn't matter in terms of naming. The main difference, ionic compounds are going to get crisscrossed, whereas covalent compounds come together in individual units called molecules, so there's no charges, there's no crisscross method, and there's no Roman numerals. Now I'll explain a little bit about the Roman numerals in a second on the metal side, because that's where it matters. So when you look at the metal in a chemical compound, for an ionic compound in particular, the name does not change. So you just name the metal whatever the metal's called. Now, as far as the business of Roman numerals go, here's how it works. If the metal that you are naming has more than one oxidation state, or I should say has only one oxidation state, like in the entire group 1, the entire group 2, this entire group 3, then you just name them and you're done. It doesn't get a Roman numeral. However, if the metal has more than one oxidation state, like Ti, so if we look at Ti, it has multiple, vanadium has multiple, chromium has multiple, manganese, iron, cobalt, nickel, copper, nickel and copper. So those guys, and there's a bunch of others that have multiple oxidation states, gold, mercury, platinum, so I'm not going to name them all, but there's a bunch. So now, if it has more than one oxidation state, then you are going to need to give me a Roman numeral in the name to tell me what that oxidation state happens to be. In other words, if the Ti in the compound happens to be +2 when you assign the oxidation numbers, then you're going to call it titanium Roman numeral 2. If it happens to be +3, titanium Roman numeral 3. And if it's 4, titanium Roman numeral 4. Be aware that the oxidation states on the periodic table, notice this word right here. I'll use a different color. Selected oxidation states. That's incredibly important, because what that means is that's not all of them. So if you get an oxidation state on a compound that happens to be outside of what's listed on the periodic table, you go with it, because this is not all of them. The ones on the periodic table happen to be the most common. Now, that's how you think of names, just like people's names. Chemical names have a first name and they have a last name. For ionic compounds, you've got your first name, which is just name the metal. It might get a Roman numeral depending on the metal. And then for the last name, we take the non-metal ending and we change it to be IDE. So fluorine would be fluoride, chlorine, chloride, bromine, bromide, iodide, or iodine, iodide, brain fart, hydrogen, hydride, carbon, carbide. You get the idea, okay? And so that's how you name it. So I'm going to do a bunch of problems on the back. So this is like a flow chart for how to name things. And now let's do covalent names, right? So for covalent, it's very simple. We use prefixes to tell exactly how many atoms are present. The reason we have to use prefixes is because the number of atoms that are present vary dramatically. In ionic compounds, they exchange electrons by transferring, and they form predictable compounds every time. So I don't need to predict when calcium and oxygen form a bond, which is ionic. I don't need to predict how many calcium and how many oxygen, or I can easily predict how many of each. Whereas, for example, when carbon and hydrogen form bonds, you can have 1 carbon, 2 carbons, 3 carbons, a billion carbons. So there's no limit to how many you can have. So you need to specifically spell it out. You've got this many of this atom and that many of that atom. There's a rule, never start with mono and no double vowels, because it sounds weird. I'm going to go over that in a little bit when we actually get some practice problems. So that's it. And then IDE, they all have IDE endings on the last name. The good thing about the polyatomic ion table is they don't change their name. Their names are found on the polyatomic ion table, and that's their name, and you've got to deal with it. So it's that simple. Let's do some practice problems. Hopefully this will be much easier. So what I want you to do is, if you have this printed out on 2 pages, that would be great. If not, take a picture of this front page and then keep it out for the back page so that you can follow along with the flowchart. So let's do the ionic ones first. So these guys are going to look like this, and I'm going to try to color code these. So these are all going to be metal, these are all metal, non-metal. Therefore, they are all ionic. Let's save a little time. I want you to write it out every time. Sorry. Not sorry. So now, with these guys, let's look at the flow chart. I'll try to have it up here. For the metal, all you do is you just name it. So sodium, or Na, sodium, Mg, magnesium, Cu, now, I'm going to skip over the oxidation state bit for a second, and I'm going to explain it once we go back. For the non-metal, we just add an IDE ending. So chlorine, all right, so let's review this, because that's almost totally correct. So for sodium chloride, that's 100% right. That's the name. For magnesium chloride, also 100% right. Common question, or at least this should be a common question. Well, why does sodium chloride have one chlorine, yet magnesium chloride has two chlorines, and why isn't there something in the name to indicate that? And the answer is because ionic compounds are so predictable, you should be able to figure that out on your own via the crisscross method. In other words, if I know that chlorine's most common oxidation state is -1, and I know that sodium is +1, when I crisscross them, I can predict that formula. And since I know chlorine's -1 and magnesium's group 2, which is +2, then I know that I crisscross them and produce that formula. So you are on your own as far as knowing that you are going to be expected to be able to understand that in an ionic compound, they have to come together in a certain way, and I use oxidation states and crisscross method to do it. Next two, here's why you need a Roman. Now those don't need Roman numerals, because if we look up sodium, there's only one oxidation state. It's always +1. That's why it's so predictable. Magnesium, it's always +2. That's why it's so predictable, it doesn't need one. Copper, though, we've got a problem. Copper is commonly +1 and +2. That's what it really means for the metals. It is very common to see copper as +1. It's also very common to see copper as +2. Can it be other things? Yes, but they're less common and therefore not listed. Now, because of that, I need a way of distinguishing these two from each other. In other words, I can't call them both copper oxide. They don't have the same chemical formula. This is where oxidation states come in, all right? So if I know my rules, this thing is set equal to 0. There's a rule for oxygen, it's -2. I multiply down, I get -2. It's going to be a little tight here. So then mathematically, copper in both cases has to be +2. But since there are 2 copper in the lower formula, it's going to be +1 each. And since there's only 1 copper in the upper formula, it's going to be +2. So watch my name. Because of this, this is copper Roman numeral 2. And because of this, this is called copper Roman numeral 1. There are a ton of common mistakes here, because most people think copper Roman numeral 2 means that there should be 2 coppers in the equation, and then they constantly write down that formula as the answer, and then copper 1, they give me the upper formula, and they flip it all the time. It is not the amount of atoms that are present. That's covalent. It is the oxidation state of the atoms, and you have to be able to understand that. So for example, the reason the copper 2, the reason the formula is CuO is because hopefully we picked up on this, that 2 and 2 reduce to 1 and 1 when we crisscross. That is true, but that does not mean the oxidation states actually change. They really are +2 and -2. What it means is it takes 2 copper to stabilize, or it takes 1 copper giving 2 electrons to 1 oxygen to make it stable. So the charges, the oxidation states are really +2, -2. But the formula is 1 and 1 because they just exchange double the amount of electrons. So hopefully that makes sense. We will do some more. Now let's do some covalent compounds before we get back to polyatomics. So for these guys, I'm doing this intentionally. These are going to be covalent, these next three. Okay, and now I want to do this this way to have a little bit more practice. So the way we do covalent compounds is we literally use these prefixes, and they're pretty easy. Mono means 1, di means 2, tri means 3. Tetra gets a little confusing, but it's not that bad, is 4. Penta, like a pentagon, is 5. Hexa and hepta get confused all the time. Hexagon, heptagon, 6 sides, 7 sides, that's the general idea. Octa, that's easy, 8. Nona sounds like 9. Deca, 10, like a deck of cards has 10 numbered cards, and then it has the face cards afterwards, and that's where it comes from. So they're not terrible, but again, they are they in your reference table? I think they are, right? No, they are not, unfortunately. These guys are not. I was thinking of the organic prefixes. They are. We'll get to them in like about 3 weeks, and we'll get a whole nother set of prefixes, and they will be less fun. But for right now, those are the prefixes we're going to be using. So the way we do it is simple. We literally just add the prefix onto the number of the element to say how many there are. So for 2 hydrogen, I say dihydrogen. Now notice, because hydrogen was the first name, right, it didn't get the IDE ending that they normally do. Next, for 2 nitrogen. Dinitrogen. And for this next one, there's just one problem. You never start with mono. So that's this part. You never start with 1. I don't know why they decided to do this. I happen to not agree with it. I think if you're going to stick to the rules, you might as well just stick to the rules. But you never start with mono. So the name is just going to be, if there's 1 nitrogen, you just say nitrogen. Okay? It's that simple. And now for the ending, I use a prefix and I give it an IDE ending. So for 1 oxygen, we would say mono, and now, again, I'm going to make a mistake intentionally. Monoxide, all right? So that doesn't sound right, right? Because think about it. What sound do cows make? Well, they go moo. How do you spell moo? M-O-O. So this would be pronounced monoxide, which doesn't sound right. What we want to say is basically monoxide, but we want to make it one word, so we have to get rid of one of the O's. That's where the double vowel comes in. It's really just a pronunciation issue. So if it's an AO, we get rid of the A. If it's a double O, we get rid of the O. I'm never going to fault you on that. I don't really care that much, but it is something you should be aware of. Now, so that one's an easy one. The next one, 6 oxygen. So we say, wrong color. Hex, it would be hex AO, but then again, it would make like an ow sign. And what we want to say is hex oxide or hexa oxide if it were 2 words. So I'm going to get rid of the A and just do that, hex oxide. The last one, trihydride. So notice, all the endings have the IDE, and the first name does not have the IDE. It's that simple. All right, let's do some more, and let's mix it up. So these next 2 are going to be metal with nonmetal, and therefore ionic. Now, the issue with these is we have a polyatomic ion, but it looks complicated. It's actually easier. So polyatomics are great. Watch. We name the metal just like normal. Calcium, copper. We check to see if the metal needs a Roman numeral. Calcium does not. It only has 1 oxidation state. Copper does. It has more than 1 oxidation state. So for calcium, I'm done. For copper, I'm going to have to go back in and figure it out. I'm going to do that at the end. And then last but not least, we look up the name of NO3 on table E. And here's the nice part. We don't do anything with it. We just write it down. So NO3 is called nitrate, right? So now, the first formula is totally done. It doesn't need a Roman numeral. It's finished. It's called calcium nitrate. The fact that there are two nitrates present is, again, it's ionic because it has at least one metal present. So although you're right, it has two nonmetals, the moment you have at least one metal, you're ionic, and you've got to crisscross this. And so when I crisscross this, that's the reason why there's two nitrates. So again, they're expecting you to understand that. It's not included in the name for ionics. In covalence, it's almost spelled out, but sometimes it is, sometimes it's not. Now, for the next one, copper nitrate, I need to know the oxidation state. So here I'm going to give you a trick here. So here's the easy way to do it. When we looked up NO3 on the polyatomic ion chart, it told me that NO3 as a unit was -1. Okay? Now, if all I need to know is the copper's oxidation state to create a Roman numeral, then watch how I do this. I'm going to set the whole thing equal to 0. I'm going to assume NO3 is one element. That's what you can do with polyatomic ions. So I have two NO3 groups. They're -1 each. So that gives me -2 from the NO3. So now the copper is just going to have to give me +2 to make the whole thing equal 0. So since there's only one copper, it gives me the whole +2. So now this is copper 2. So when we did oxidation states, I made you do NO3 separate, and then I had you find the N, plug it back in, solve the whole thing, and then do the copper. Now I'm showing you a way to get to the metal faster, because for this type of question, I don't care about nitrogen. I don't need it. I just want the name. Now, if I was doing in our later unit and I actually needed to know the oxidation state of that nitrogen, then I'd have to be able to do the full way that I showed you the other day. But until we get there, you can skip it and do it this way. Next three. These look like they have lots of elements, but they are all nonmetals, so they are covalent, okay? Because again, nonmetal, 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 the same here, the same here. So be aware that the polyatomic is present. There's no parentheses around them because there's only one of them, right? Because there's one of them. We can drop the parentheses and they drop the 1. So they're not drawn that way, but just be aware that they are the polyatomics. So now I just need to say 1 hydrogen, 2 hydrogen, 3 hydrogen. So I don't start with mono. So I just go hydrogen, dihydrogen, trihydrogen, no IDE ending, it's the first name. And then for the polyatomic, I just write their names down. Carbonate, sulfate, phosphate. Now, common mistakes. Do not confuse carbonate with carbide. Carbide is carbon, carbonate is CO3. Also, do not confuse sulfate, to look at the endings. Sulfate is SO4. Sulfide is sulfur. Phosphate is PO4. Phosphide, IDE ending, is just P. So don't confuse those. Those are very common mistakes. And then the last set, we're going to go backwards. So these shouldn't be too bad. So these three are ionic. So is this one. And then these two in the middle are covalent. The reason I knew that is because I know tungsten's a metal, oxygen. I'm just more familiar with the periodic table. So I know tungsten's W, it's a metal, oxygen's a non-metal. I know yttrium's a metal, Y, sulfur as sulfide is a non-metal. As soon as I see a Roman numeral, I know it's automatically ionic. As soon as I see di or penta or tri, any of the prefixes, I know they're covalent. And then this one, again, magnesium is a metal and nitrogen's a non-metal. Also, don't confuse nitride, IDE ending, with nitrate. That's another common one that gets messed up. So those are the last ones, and then let's do them and we're done. So for tungsten, tungsten is, I'm going to write it over here, W, and oxygen, O. I have a rule for oxygen, it's -2. I do not have a rule for tungsten. So, and the whole thing, I don't have the formula, so I can't set it equal to 0. So here's what I'm going to do. I'm just going to look it up on the periodic table. Tungsten's normally +6. Okay, so what do? I put a +6 in because that's the most common form of tungsten. And so I'm just going to go with what the periodic table tells me because I have nothing else I can really do. So now I'm going to crisscross them, but don't make a mistake. 6 and 2 can be reduced to 3 and 1. And then when they're crisscrossed, the formula is W3O. Next one, yttrium and sulfide. Sulfur is S, it's -2. The reason I'm able to do that so quick, just in case you know, I know that sulfur is right under oxygen. And since I know oxygen's -2, well, guess what the first number for sulfur is? It's -2. Now, another question I get asked a lot. Well, nonmetals have a bunch of oxidation states. Why don't they get Roman numerals? Well, because nonmetals are pretty predictable. With very few exceptions, they're always going to do the octet rule. So they're always going to do the very first one. So again, they're more predictable. I don't have to worry about it. The metals that have multiple oxidation states, they are not predictable. They very frequently do all the different oxidation states. So you can't just count on them doing what you would expect. Whereas the nonmetals, they're pretty consistent as well. And so sulfur is S, it's -2. Yttrium is Y, it's +3. That's the only option. Crisscross them, and my formula is Y2S3. So that's how you do these. Next one, manganese dichromate. Sounds complicated, and you thought you said that if it has a di, it's automatically covalent. There's an exception there. So let's do it. Manganese is Mn. Manganese has lots of oxidation states. Which one do I pick? Well, guess what? They told you right there. They said manganese was 7. So, +7. Now, next part, dichromate. Well, that's not an element. Chromium is an element. Chromate is something else. Now, based on the ATE ending, if I look at that ending, right, the ATE, that's going to give me a clue. It's on table E. So chromate is CrO4 -2 charge for the whole molecule. Dichromate is Cr2O7 -2 charge for the whole molecule. So the way I do that is I write Cr2O7 -2 for the whole thing. I'll put parentheses around it. So now when I crisscross it, this 7 tells me how many dichromates I need, and this 2 tells me how many manganeses I need. So it's going to look like this. Mn2 parentheses Cr2O7, close the parentheses, 7 again. So that's a big element, or big compound. There's lots of atoms in that, and that's because the manganese was 7. Now notice it's 7 and then 7. That's just coincidence. Again, a common mistake is to think that this 7 is fine. If I leave this 7 off, it's fine because there's a 7 there. Doesn't work that way. Cr2O7 is the polyatomic. That can never change. The only thing you can have is multiples of them, and the way you do that is by putting numbers outside parentheses. Let's do the last ionic. Magnesium nitride. This one's easy. Magnesium is Mg. Nitrogen is nitride. Nitrogen is -3. First oxidation state. Magnesium is +2. Crisscross method. Mg3 and 2. Easy. All right. Last two, covalent. I saved the easiest for the end. Here's the reason why it's so easy. They tell you exactly how many of each you need. Dihydrogen dioxide, that means 2 hydrogen, 2 oxygen, so H2O2. Sometimes I'll have people say, well, but why didn't they reduce? They're not ionic. That doesn't happen. That's actually the reason you can't use the crisscross method on covalent compounds, is because, just to give you a quick detour, while water can do this, right, H2O, we should know that, it can also, H's and O's can also do this pretty common. That's H2O2. So because covalent compounds can do this, or they can do this, or though technically there's no limit to how many O's you could put in the middle, they can do all sorts of weird things. They don't follow the crisscross method, so you can't just reduce them if possible, because they frequently don't always reduce. Ionic compounds, however, always reduce. No exceptions ever. Last one, phosphorus pentachloride. So the fact that they didn't write anything here means that it really was a mono that they intentionally left off. So therefore, it's phosphorus, and then pentachloride just means 5-chlorine. Done. So we're going to do this is just the notes. We're going to do a bunch of practice with this. We're going to do some practice in class, and we're going to do a naming lab where we basically have a bunch of mixed chemicals just like this, and you're going to have to pretty much do one of these, but for a lot more, and we're going to go over it and spend a lot of time on naming.